Welcome back. So video number 13, the second class of the span, basis, and independence and dimensions. So the definition of the dimensions is the number of bases. So if you think about a line space or R1 space, and that is 1D space, only has one basis. So any line can be expressed as it's only one basis. So let's say if U is 1 minus 1, then the whole line can be expressed as linear combination of A. So if you multiply any number with this vector U, then you can express any number. So any number in R1 space. And if you think about a plane which is within R2, so it's 2D space or plane, it needs two bases. The most common, the widely known two bases are going to be the unit vector along x-axis and y-axis. So one example, the most common basis for plane is unit vectors along x and y-axis. So if you think about the x and the y-axis, then unit vectors are defined as I 1 0, and then here j 0 1. So in 2D plane, 2D space or plane, we only need two bases, and they are all independent. So we can make any linear combinations between these two vectors to span a space R2. Right? So this is a linear combination. And then the third one is a volume. So this is a 3D, I'll just follow the previous ones. Within the R3, that is 3D space. So because it's 3D, you need three bases. Okay. And then the most important, widely known three bases are going to be I, which is going to be 1 0 0, and j, this is the second basis, and the k is going to be the last basis. So these are three widely known bases, but you can select any basis you want by changing each and every elements. Okay, so then let's go ahead and define find some of them. So basis, again, I will emphasize this, for a space must be one, independent with each other, and ijk's are all independent because any linear combinations using these three bases or three independent vectors can span a volume or 3D space, which is the definition of the linear combination. Okay, and the basis must span a space. Okay, so this is the condition for the basis for a space. Okay, so then the one example is going to be in R1 or the line space. If I define a vector u, which is 1, and then v, which is -2, then how can we define a basis dimensions and whether they are span or not, cannot span other space? So first, are they spanning the line or R1 space? Are they basis for this line? What is the dimension of this R1 or line? So the sets of the vector u can span this line because any linear combination with u can be line. Is this basis? Yes. Then what is the dimension? 1, because we only need one basis. And how about the sets of v vector? Yes, it can span, and v is a vector, the basis, and so dimension is 1. And how about the sets of vectors u and v? They can span a space? Yes, of course. And are these two vectors bases? No, we do not need more than one basis. So still, its dimension is 1, right? So these are some simple examples. Okay, so then what about the 2D space? Let's consider a R2 space which is plane. Then we can define three bases or 33 vectors. So number 1 can be 2, 1, and v vector can be 1, 3, and we can also define another one, w vector, which can be 3 and 3, right? And then we can also think about, are these vectors can span a plane, and are they a basis? What is the dimension of this space R2? So the set of vector u can span a space if you only have one vector. Then this vector only can span a line. So it cannot, only a set of one vector cannot span this plane. So it cannot span a plane. Is this a basis? No, because we need more vectors. And then what about the sets of u and the v? Yes, it can span a space because any linear combination between these two vectors can make 2D space. So they are basis, so the dimension is 2. And what about the combinations of u, v, and w, 3 vectors? They can span a space? Yes. They are redundant, but they can span a space. But they cannot be the basis because they are redundant. And so the dimension is 2. Okay, so this is the concept of the basis span space, independent vectors, and the linear combination.